Okay. Uh, well, today we will talk about this theorem of the lecture notes, the
Mm-hmm.
theorem 223 by Pecati and Tudor. Okay, it's about well, multivariate Gaussian approximation. Well, here we have the hypothesis that d is greater or equal than 2. Here we have this constants q1 until qd, and here we have a random vector, okay, where its component is a stochastic multiple integral. Its component of the vector fn,
Mm-hmm.
and these functions fn, well, f power 1n until f power gn are square integrable and symmetric. Okay, and here we have this hypothesis about the convergence of the second moment. Okay, this hypothesis we will use it for for having the timex for the for, for the vector fn. Well, here we have the result. These two conditions are equivalent. Uh, well, here we have that fn converges to a normal, to a normal random vector in law, and this is equal to, or is equivalent to say that each component of the vector converges in law to a normal random variable. Okay, uh, and the proof that we will be showing is a proof that is in the book of Noalart, the red book. Okay,
Mm-hmm.
mm, well, let's start.
Of both Muhammad, father and daughter.
Ah, I didn't know
The book.
that.
Yeah, Eulalia Nualart is daughter of
Ah,
David.
interesting, interesting.
Yeah, yeah.
Here we have theory 223 of the lecture notes. Mhm. Well, I'm going to write here some the hypothesis. Uh, well, you have a random vector. Its component is a multiple stochastic integral. Q1 is the order. Okay, the order. Uh-huh. Also, we have that each of these functions are symmetric and belong to this space. Here we have the hypothesis, the about the convergence of the second moment. Okay, this converges to this uh, when n tends to infinite. Okay, this this happens for every e between 1 and d. So we should prove this equivalence. Okay. Well, we only prove that 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 2 implies 1. Okay. Okay. It's enough to prove the 2 implies 1. Okay, this is 1 and this is 2. So let's start. We claim, this is the first claim, that this sequence of vectors of random vectors is tight. Well, we will use this hypothesis to justify that this sequence of random vector is tight. Okay, this is the reason, because they have, well, the second moments are the second moments of the coordinates of this random vector is converging, no, to sigma square of I. So so it's enough to show the limit in distribution of every subsequence of that every convergent subsequence is a normal random vector, no? It's enough to show that the limit in distribution of every convergent subsequence is a normal random vector. Okay. I think this is a theorem in the Durret's book, in the last edition. This is the theorem 3.2.13. Okay, so so we can assume that this sequence converges in law to this random vector. It's a limit random vector. So it remains to prove that this limit, the distribution of this limit vector is normal. Okay, so that's the idea, no? That's the idea to show that to show this. We will use characteristic functions. Okay. Okay. So for for n natural and t element of this space, we define this. Okay, this is the characteristic function of the random vector fn. We will be working with characteristic functions, and bar phi of t is the characteristic function of the vector f infinite. Okay. So for all j between 1 and d, we have this. We compute the partial derivative of the characteristic function bar phi n with respect to tj. Well, this is equal to I, and here we have this. Okay, this is just a simple calculation. Okay. But remember that fn this is we have this, right? That fn is converging in low to f infinite. So this, when you take the limit of this, well, this part is converging to well, we have this. Okay, but this is equal to the partial derivative of bar phi with respect to phi. Okay, this is the equation 2. We'll call it 2. Okay, so this is the first part, and the other part is to show that, let me see here, let me see my notes. The idea is to prove that this is equal to this. Okay, so we will prove that this expression converges to this expression, and well, and then we are done. So this is the idea. Okay. Okay. So here we have to remember some previous concepts. We will use the definition of the operator L, Okay, also we will use proposition 152 of the lecture notes. Okay, and also we will use the duality between d and delta. Okay, let me show you that the definition, those definitions is it's here. Just to remember. Okay, okay, remember that L is an operator. Okay, is the infinitesimal generator of the Einstein-Uhlenbeck semigroup. This is the definition. Here we have something important, that this the random variable belongs to the domain of the operator if and only if this expression holds. Okay, this is important. And then we have the proposition 152, that if you have a random variable in L2, then we have that f belongs to the domain of L if and only if f belongs to D1, 2, and the derivative of f belongs to the domain of delta, and in this case we have this expression. So we will use this. Okay, we will use this equation, this property. Okay, also you have to remember that this equality is true when f belongs to the domain of L. Okay, and f belongs to the domain of L if and only if this inequality holds. Okay. Well, so we will work with this expression here. Okay, okay, here we have the expectation of f and j. Here we have the characteristic function. So this first equality I will justify later, but you have to use the proposition 152. Okay, I will justify later. This is equal to this. This is okay. I will prove this later, but basically I am using the proposition here. Okay. Well, I am using the definition here. Sorry. For the second equality, I will be using the proposition 152. proposition. This is equal to this. Okay, this is minus delta d of f and j, and here we have the characteristic function, well, the exponential. Then we use the duality. We have this. Okay. Well, then we're going to do some computations. Okay, this is well, this is a property that is not hard to prove, that the derivative of this, of this expression is equal to this, the exponential of I inner product Tfn I, and here we have a sum dh and d f and h. Okay, this is ph, this is h. Okay, so you use this property. Okay, this is equal to, by this property, this is equal to this. Okay, y acá I have the finite sum th df and h. This is okay. This is equal to I over q j okay. This I take out, I take it out. Okay. Okay, this exponential I take it out outside the inner product, and we have this. Okay. Okay. Then I going to take out the sum. I'm going to take it. Okay, I'm going to do this. I'm going to take it out the sum. Okay. Here we have this. This is the sum from h equal to 1 to t, th, in here I have this. Okay, so this this term I will call it gamma g gamma power gh fn. Okay, well this is the this is the element of a matrix called Malevin matrix. Okay, so we have this is equal to this. Oh well, I'm going to take it out the sum, and we have this. Okay, well, so finally what we have that this derivative of bar phi n with respect to tj is equal to I multiplied by all of this. Okay, so
Wilson,
see,
sorry, it's missing th.
yes, see, uh, yes, yes, it's missing th. Okay. Yes. So this implies that the partial derivative of bar phi n of t is equal to minus 1 because you are multiplying I by I. And you have this. So now we will work with this term. Okay, we will work with that term. Remember that, oh well, in the book, in the red book of Noah, this is the Malevin matrix. Okay, the Malevin matrix. So well, something is missing. Yes, this is missing. I have not justified this equality. I'm going to prove it now. Okay, Well, uh-huh. Mm-hmm. Okay. Well, uh, let me show here. Okay. Yeah, okay. If you have this, that f has this form, okay, this form, and if that function f belongs to the domain of L, no, no, this function f belongs to the domain of L if and only if this holds. In that case, you can compute L of f, okay. So okay. Mhm. We have this. I don't know if I am right, but we have that fn j power j is this. Okay, but here you have that f is a infinite sum. Okay, so um, I don't know if I am right. You can express this multiple stochastic integral like this. Where qk is 0 if q is different of j. Mhm. Okay, so if we prove that f and j belongs to the domain of L, this implies, okay, by this statement, okay, see the function f belongs to the domain of L. You can calculate L of f. We have that you can calculate this, okay, and this is equal to this. But remember the index. This is equal to minus 2j f. Okay, so I think that we have to it remains to prove this. We have to prove this. So let's come back. To prove that f belongs to the domain of L, you have to prove that this series is convergent. So, but this series, okay, we are going to analyze the series. This series is well, mhm, mm, uh, let me think. Well, by the way of by the form of fnj, we have this this series reduces only to one term, right? mm, okay, so this is true, because because of this. Okay, that infinite series reduce only to one term, to this term, but this term is finite, because well, this is equal to this, this is equal to this, mm-hmm. But by hypothesis, these functions, well, the norm of these functions is finite, no? This is the hypothesis here, is because of this. Well, so mhm. Then I take this this part, mhm. We have this, we have this. Well, that's the way how I have proved that equality, the equality one, that is in white blue, in sky blue. Okay, because you have this. I have proved the function fnj is equal to minus 1 over 2j multiplied by L fnj. Okay. So let's come back where we were. We were here. Okay. We are going to analyze this term. So we have two cases when j is equal to h and when they are different. Okay. So So claim 2, for G and H between 1 and D, we have this L2 omega. We have that this term converges to 0 in L2 when G is different of H. Acá it's missing the H. And also we have this when when G is equal to H, this term converges to Qj sigma J square in L2 where n tends to infinite. To prove 4 is easy because because our hypothesis, and also we have to use this theorem. We will use this. Okay. So let's come back. For it follows from condition 3. Okay, condition 3 of this theorem. Okay, of theorem T22. Okay, because of this we have this, that the norm of the derivative of fnj power 2 converges to qj sigma square j. But remember, who is this? This is an inner product of the derivatives. It's here. Okay, but this is equal to the inner product of this. Okay, and this is equal to, and this converges to this. Okay, so the most difficult to prove is 3. This is the hardest to prove. Now let's prove 3. Okay, so suppose that G is less than H. Okay, without the loss of generality. So we want to analyze this. Okay, so we have to verify the convergence in L2. So we compute the expectation of this. okay, power 2, but this is equal to the expectation of this inner product, okay, power 2 in H. So well, remember that these these terms are stochastic multiple integrals, okay. So we have this is this derivative f and j, no, the derivative of this integral of this multiple integral of order qj of f and j, the derivative of this. I'm just replacing, okay, I'm just replacing. Then you compute the derivative, and you have this is qj minus 1 f and j, okay, this is qh iqh minus 1 of f and h of this, okay. I'm going to take it out these terms outside. We're going to take out these terms outside. And here we have this. We have this. We have this. We have this. Okay. So okay, here we have to use some properties, but well, but first let's disappear the inner product.
Something fixed here? I'm not understanding.
How?
T is fixed. Ah, no, I see now because you to this one. Yeah. Okay, sorry. No, I understood. You went to.
Okay. Let's disappear the inner product. Well, this is an integral, right? This is the integral. Well, here we have the expectation. Here we have the integral. Well, here there's something strange here. Yes.
Don't you have a? I'm not understanding this first line here.
Here?
Don't you have an integral? No, the first one. The second inequality. Equality, yeah. So don't you have a? So what is t? Where you? Don't you have an integral? I'm not understanding.
Well, here I am.
T.
I am
T.
confused.
What is t? T is you are integrating t. This bracket is the integral in t.
This?
Where is the integral in t here? Is this bracket? No. I'm confused. I got confused here because I don't understand. There is this derivative and
Well, here we are just computing the derivative.
yes, and the bracket is the integral in t. So this bracket in the second line involves an integral in time, no? Yeah, I guess so.
Okay. There's something here.
There is somewhere the time.
Okay. There's something strange.
Yeah, maybe it's.
Maybe just notation.
I'm not understanding the t there. So, or there is an integral in t, or I don't understand.
Let's come back here.
Yeah.
Well, this is the first time that we compute a derivative.
So,
here.
yeah, the derivative is this when I evaluated t. So that bracket there involves an integral in the time. The bracket which you have there, because here is dt. So here you have d, and this bracket. So do you have an integral in time? This second bracket means an integral in time.
This is an integral.
In time, in t.
Yes.
Ah, okay. So that was my question. Yeah, okay. So then it's okay.
Okay.
Okay, I understood. Thank you. Sorry, but I got. So it's perfect. Yeah.
Yes. And we have this. But this is power 2. And here we have to use some properties that we have seen before. Is equation 118. This, yes, these two. Okay, and the other is this. Okay, so okay, let's continue. This is equal to this. Well, this is equal to this. This is a sum of this. This combinatorics. And here we have this tensor product. Okay, here there's something. Yeah, here in the book you have this, no, r plus 1. Okay, okay, here is r. Well, that's because you are taking an extra integral here. Okay, you have an extra integral, and that's because you have r plus 1. Okay, here is just the product of these integrals, of these two integrals, but here you have the integral of the product of these integrals. Okay. Then you have to compute all of this expression power 2. And this is equal to this. And we will be using here this property, this. Okay, when the index are different, some terms vanish, so we have this. We have this. Here we have the norm. This is because property 118. Here we have the symmetrization. Okay, so you have to put here the symmetrization, no? Power 2. Okay, then we change the index. We change the index. Okay, here we start from 0, from 0 to 1. Here we have -1, -1, factorial. Here we have just -2r. Here we have r, and here we have this minus. Okay, here we use a property that we have used before, but without proving it. There is a property that this is less than this. Okay, we use this. So all of this is less than. Well, I have to copy all of that. Okay, and here I change this. Okay, so so we have to prove that this term goes to 0. That's the way to prove that term goes to 0. Okay, so let's prove it. Okay, we have this. Here, well, this is equal to this. Just the inner product. Okay, okay, just the inner product here. Okay. So here Noalar use a property that I think it is based in, I don't know, maybe in Fubini theorem. This is equal to this. Okay, this is the property that Noalar use. it looks like a factorization, I don't know. And then you have to use Schwarz. You use Schwarz. Here we have this. This is less than this. Uh-huh. Okay, so now we will prove that this term goes to 0. Okay, for to do that we will use again this theorem about the 4 moment. But the property for condition 4. Okay, this condition 4. So we have to adequate what we have by theorem 2 to 2 4. We have this, no? That for all r between 1 and QH minus 1, we have this. Okay, where n tends to infinite. But as we have this, okay, we have this, so we have this. We have this. So this implies that the norm converges to 0, right? Okay, and we are done. Because we have proved that this, we have proved this, no, that this converges to 0. That means that this term gamma fn gh converges to 0 in L2. So so finally from 3 and 4 we have here 3 well, there is a lot of computing here. Okay, so we have that this that depends of t. Okay, we prove this, right? We prove this. Okay, we proved this at the beginning, but also we have proved that this converges to q j to this term, right? Okay, this is by 4, and the other terms converges to 0. Okay. So the other terms converges to 0, and this term converges to qj sigma j square. Some term vanished here, and we have that all of this converges to minus tj, okay, bar phi of t sigma square j, okay. But also we have this so the limits should be equal. Thus we have this is equal to minus t j, okay, for all j between 1 and b. Okay, this means that bar phi is the characteristic function of a normal random vector. Okay. Well, and that's all of the proof, because the other condition is that we have proved that 2 implies 1, okay, and 1 implies 2. Okay, I think that it's easy to see, okay, because of, I don't know, the Kramer-Wald device, I think.
No, that's general, no?
Oh, yeah, right.
Just you take ti is equal to 0 in other places. You take 1t, you just take the characteristic function at t, one coordinate t and the others are 0. I mean, this is general. Okay. The marginals converge.
So, and that's the that's a proof of Noalat, because Pekatin Tudor has another proof.
Yeah?
Yes, I was reading the paper, but it's another way, I think.
Yeah, maybe this is already elaborated, so the original. I didn't understand very well this point you made here, because I understand it's probably trivial, but I got lost because I am not very the point where you made the sign where there is some integrals
here,
so you have this one, and what it is, you integrate some variables
here.
Yeah, this one. I don't want to prove it, but I just want to understand what does it mean. So here you have R, and R is less than Q, no? And what you did here, From here to here, I'm a little bit lost.
Okay.
Anyway, but I can check afterwards because this doesn't appear to be too. Maybe I forgot something.
Well, that I was trying to prove that, but I couldn't.
So when he doesn't, he says as if it were trivial. Maybe there is somewhere in the book. Okay. There could be that. It could be that this is because they write as if it were trivial, no?
Yes.
Yeah, because maybe somewhere in the book they state and we are not. Because to me it's not so clear what does it mean. It's not even that I believe, but I don't understand. I don't understand it either.
That's weird.
So this is the integral in so h to r h to r. Yeah. Anyway, but that's not. I don't think we need to see it now. I will check it to see if I understand. There is. I will check it afterwards just to see where is the point that I don't understand. But I have another question which is probably stupid, but I want to ask anyway. In the theorem, the Q's, you cannot have two elements with the same in the same chaos. The Q's have to be different.
Yes, the Q's are different.
So yeah, they have to be different for this theorem. So, but it's do they comment what the, because or do I say something nonsense? Because to me it seems that from the it would make sense to take two different functionals of the same the same cows, the same order, no? Probably maybe it doesn't apply or it's trivial. That's my question. Do they comment something?
No.
So maybe, yeah, maybe it's trivial or I don't know. I don't think it's trivial because it makes sense, no? It makes sense to look at a vector where I have two integrals of different functions of the same dimension, no?
Yes.
But maybe what I'm saying is nonsense because maybe using the fact that it's an integral you could reduce to one only. Yeah, probably what I'm saying is nonsense. You can always reduce to one, probably. Because it's an integral. Yeah, probably I'm saying nonsense. Yeah, I think it's nonsense. Yeah, that's interesting. Yeah, thank you. So, I think you are done for today, no?
Yes.
So my question is the following: do we have two more meetings or one? The calendar goes until when? Until 14? No, 13. So we have two meetings. Then it's okay. I thought we have only one, and then it would be a little bit unfair with Rodrigo because Rodrigo